So we've talked about alkenes and their isomers and of course their naming. We talked about the bonding in them. Okay, here is of course the simple bonding. What we saw blue is the sigma bond. That's where two electrons are being shared that we think of as being any old single bond. Nice direct bonding between the two nuclei. And then the pink above and below are of course the pi bonds formed by the overlap of a p orbital that's pointing up and down on this atom and a p orbital that's pointing up and down on this atom, just overlapping nicely. The sigma bond part, those electrons are held more closely and more tightly to the nuclei, so they are stronger than in the pi, where the electrons, yeah, they're held by the nuclei, but they're not nearly as nice, nearly as tight. Now, of course, the electrons, and I've just put slightly negative there, probably should actually just call it negative, but those are electrons in that pi cloud above and below the bond. Okay, and of course, what are electrons? They are negative. Negatives like positives. Fancy word for something that likes a positive is a nucleophile, right? Nucleo comes from the idea that the nucleus of an atom is positive, phile, loves or likes, right? So negative things are going to be called nucleophiles. Not just negative things, anything that likes a positive is a nucleophile. Now, of course, what this means is that the electrons in this electron cloud, being negative, reacts with positive things. And positive things, of course, like negative things. What are negatives? Electrons. And so positive things that like negative things are called electrophiles. So these are two really important words that you need to be thinking of all the way through. Nucleophiles are things that like positives. Electrophiles are things that like negatives. Now, most of the reactions that alkenes do, certainly the reactions we're going to focus on, are addition reactions. That is where an electrophile comes up to this electron cloud, which is kind of just like a spare bond for this carbon-carbon atom, and adds across it. The electrophile uses the electrons that were in the pi cloud to make new bonds to bond to the carbon atom. Now, I've got a fun little animation just to illustrate that. There we have our carbon-carbon bond with the sigma bond that is pretty much going to remain in violet, and then those pi bonds, the electron clouds above and below the bond. And here we have an attacking species, and I've drawn it as being a polar bond. There are times when it's truly a polar bond, the first example we see. There are times when it is a induced polar bond. But anyway, here we've got this X atom that's slightly positive, and if it's slightly positive, that means that it likes negatives. It is an electrophile. And then here we got this Y that's slightly negative, that's right now rather boring. And so the X, the slightly positive, sees these electrons, says, I am an electrophile, I like negatives, and so starts to get attracted to it. Now, the way that we depict that is we say that it's not so much that the slightly positive X gets attracted to the electrons, it's that the electrons get attracted to the slightly positive X. So let me animate that a little bit further. The electrons from this pi cloud get attracted to the slightly positive X and so start to form a bond towards that X. Now, what that means is, first of all, there's no electrons left down here, but it does mean that, of course, this carbon atom that was having a nice little share of the electrons in the pi bond now doesn't have those anymore, so starts to develop a positive charge. Now, as those electrons from the pi cloud start heading towards that slightly positive X, it's not slightly positive anymore. Indeed, it is forming a bond. And of course, if it's forming a single bond, that means that it's making a sigma bond. Okay? And now at that point, this X says, hey, I've got my nice bonds with this carbon. I don't need you anymore. Why? Why don't you go away? The Y says, fine, I will go away, but I'm going to take the electrons that I was sharing with you and keep them. So that means that the Y becomes a full-fledged negative. Okay? Now we have an intermediate here that is called a carbo cation. It's a cation where the positive is on a carbon atom. So here's the positive, and of course positives are electrophiles. Here's an anion that's a negative. Negatives are nucleophiles. Okay, so what's going to happen here is this negative, which of course is still floating around this whole molecule, because until recently it was bonded to X. This negative says, ooh, that's a positive, let me go get that. Takes the electrons, makes a bond with the positive. So now we've gone from having a sigma bond between the two carbons and a pi bond to where we've still got the sigma bond between the two carbons, but now we've also got a sigma bond to two other species. We've gone from the double bond between the carbons to a single bond between the carbons. Now, if I show this a little bit more generally, here is a general alkene. Notice I've got R1, R2, R3, and R4 to illustrate I don't really care what's bonded to these carbons for now. I will in a minute. And R is used for the remainder or residue or rest of the molecule. So here is our standard little alkene double bond. Reacts with XY to add the X and the Y across the double bond, to add the X and the Y to the two carbons that were double bonded. That's why these are called addition reactions. There are lots of things that add to a carbon-carbon double bond. We're just going to think of 3 reactions when we're on the WJEC specification. In the extension topics, I talk about a couple more. But one of the most famous, the classic reaction of alkenes is so-called hydrobromination, and the name gives it all away. You're adding a hydrogen and a bromine. So here's the general reaction, SRR1, R2, R3, R4, reacting with the HBr. It adds across that double bond, so the Br goes to one carbon that was part of the double bond, and the H goes to the other carbon that was part of the double bond. Now I'm going to use hydrobromination. I could just as well have done hydrochlorination. Doesn't work with HF, it's too vigorous, doesn't work very effectively for HI. But for HBr and for HCl, so in other words, to turn an alkene into a bromoalkane or a chloroalkane, very nice, effective reaction. Now, it's called a regio-specific reaction because there is a very, very clear-cut way in which the atoms go on. Now, let's just to start illustrating that, consider but1ene. How does but1ene compare to just our normal one? We got hydrogen, 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 but the left-hand carbon has an ethyl group on it. That's the carbon 3 and carbon 4 of the but part of the molecule. Now, because we've differentiated between our two carbons there, I could have done it up here, but I want to do it where we've got an actual example. I've differentiated between these carbons. The left carbon is different from the right carbon. So let's react up but1ene with HBr, and you could get 2 possible products. Because what we're doing is we're adding a hydrogen and a bromine across the double bond. We could put the hydrogen on carbon 2 and the bromine on carbon 1, which would give us 1 bromobutane. Alternatively, we can put the bromine on the left hand, carbon 2, and the hydrogen on the right hand, carbon 1, to give us 2 bromobutane. Right now, doesn't look like there's any reason why one should be better than the other. But imagine the surprise of these early chemists, mostly Russian chemists, by the way, back in the 1800s, when they found that you didn't make any 1-bromobutane. All the product was the 2-bromobutane. They found that bromine adds to the more substituted carbon, and this is the first statement put together by a Russian chap, Markovnikov, thus known Markovnikov's rule. In this case, the bromine adds to the more substituted carbon, so the bromine adds to the carbon that's got the ethyl group on it, rather than to carbon that only has 2 hydrogens on it. That's what more substituted means, the more stuff you have around it that's not hydrogens. Okay, it's actually a more extensive version of Markovnikov's rule, which is that the more electronegative atom adds to the more substituted carbon. But we won't worry about that here. We might touch on it in the extension. Now let's see if we can't come up with a reasonable mechanism that would explain this. So there's the but-1-ene, carbon 1, carbon 2, and then C3 and C4, part of the ethyl group. Drawing it flat on. Okay, so you've got the two hydrogens coming out at us, the ethyl group now depicted as a big red ball, and the other hydrogen going away from us. So the whole molecule, as if we drew it and then rotated it by 90 degrees. What that means is that we can see very easily what happens when the HBr molecule comes up here. So the bromine, big green ball, the H, little sort of golden ball is what it's supposed to be. Polar bond, bromine more electronegative than hydrogen, so slightly negative bromine, slightly positive hydrogen. Now, of course, when you have a slightly positive, then the electrons in this double bond, the electrons in the pi cloud that of course are above and below, start getting attracted to it. And indeed, the electrons, they're now less likely to be below than they are above because they're getting attracted to this slightly positive. Now we depict this whole thing using a so-called curly arrow mechanistic depiction, which is where we're showing what the electrons do. So the first thing we would show is we've got electrons in this double bond that are now going to be attracted to that hydrogen, and we show that with a little curly arrow. Now this is going to make a bond between one of these carbons and this hydrogen, taking the two electrons that were in this bond and moving them to be bonding to that hydrogen. At that point, the hydrogen tells the bromines, don't want the electrons in this bond anymore. Why don't you take them with you? So this is a heterolytic bond cleavage. Both electrons from the bond go on to the bromine. Now at that point, the bromine just becomes a bromide, and we have a bond between one of the carbon atoms here and this hydrogen, and of course there is now only a carbon-carbon single bond. Well, the thing is, first of all, which carbon does this hydrogen go with? Well, could be either of them. So let's draw it first of all that the hydrogen bonds to this carbon, carbon 2. So the ethyl group and the hydrogen get pushed away a little bit as it makes this bond, and now carbon 2 is tetrahedral. But of course, poor old carbon 1, it used to have a bond as part of this double bond, but now it doesn't. It's only got a single bond. So it's lost those electrons, so it's positive. Okay, this is a carbocation with the cation on carbon 1. Now the other possibility, of course, was for the hydrogen not to go on carbon 2, but to go on carbon 1. So it does that. There's the hydrogen now on carbon 1, pushing away the other hydrogens, because now this carbon is tetrahedral, and now carbon 2 is where the positive charge resides. So we have carbocations galore as our intermediates. This is a carbocation mechanism. Now let's look at those two carbocations. The one where the hydrogen went on to carbon 2, thus leaving the positive on carbon 1. This is a primary carbocation. This carbon atom that has the carbocation on it is only bonded to one other carbon. Over here, of course, this carbon atom, it's bonded to two other carbons. So this carbon atom, and thus the carbocation, are secondary carbocations. Now you might remember when we did the radicals, primary radicals were the weakest, the least stable, secondary better, tertiary best. Same series for the carbocations. Primary carbocations, really weeny, not very good at all. Secondary carbocations, nice and stable. Tertiary carbocations, which we'll get to later on, really nice and stable. So this is the better intermediate by quite a way. And the more stable intermediate is the way the reaction is going to go. So the last step is, of course, we've got that negative there, positive there. The negative is going to bond to the positive. But now we can think about this in two ways, because this is just a flat molecule. This bromide is still hanging around, but the bromide can attack in two ways. It can attack from the top, or it can attack from the bottom. Let's see what happens for both of those. So here we are, we're considering it coming in from the top. So as it comes in from the top, it's going to push the ethyl and the hydrogen down, and we get this picture here. Okay, make sure you see what I'm doing here. Nothing happening on carbon 1. Carbon 1 is set. There's the new hydrogen, the pretty little gold hydrogen at the top, the two original hydrogens there coming in and out. Then on carbon 2, the bromine's coming in on top, so there it is bonded in on top, so it's pushed the methyl and the hydrogen away. That's one possible molecule. Or could have come all the way down and attacked from this direction. If it attacks from this direction, now the bromine is coming up from the bottom. Okay, so it's going to push the ethyl and the hydrogen away towards the top. So here is that new one. Again, carbon 1 unchanged, bromine now coming in from the bottom, pushing away the hydrogen, pushing away the ethyl group. Okay, now it might not look like it, but these are two different molecules. They got the same formula, so they are isomers. They have the same connectivity. Carbon 1 goes to 3 hydrogens, carbon 2 goes to a hydrogen, an ethyl and a bromine. Okay, but they are enantiomers of each other. They're mirror images that are non-superimposable. Well, how the heck can I tell that? Well, the first thing I would do is I would say, look at carbon 2 now. Carbon 2 has a methyl group, an ethyl group, a bromine and a hydrogen. It's a chiral carbon. Same thing here. It's a chiral carbon. It's got a methyl, an ethyl, a hydrogen and a bromine. So if it's a chiral compound, then we can assign its absolute configuration, which is the fancy way of saying R or S. This one is the R. Okay, it's 2-bromobutane. They're both 2-bromobutane, but this is the R. Now, if you remember how we assign these things, ideally, we'd like to have it so we got the lowest priority away from us, which is the hydrogen. We got it coming out at us, but as we actually discussed in the live stream and on the video that accompanies that, that's no big deal. Let's assign our priority, shall we? Okay. We have this carbon is bonding to a bromine, a carbon, a hydrogen and a carbon. So obviously the bromine is priority number 1. The blue ball is an ethyl group, whereas this is just a methyl group. Ethyl is higher priority than methyl. So when we count it, we go priority 1, priority 2, priority 3. So we're going counter or anti-clockwise. Okay, well, anti-clockwise, if the hydrogen is pointing back, is going to be S. But anti-clockwise, if the hydrogen's coming forward, is R. Okay, now let's look at this one here. And again, bromine top priority, ethyl second priority, methyl third priority. We're going clockwise. If the hydrogen was going away from us, clockwise would be R. The hydrogen's coming out at us, so it's flipped, so clockwise is S. So when we do this reaction, okay, of the hydrobromination of an asymmetric alkene, in this case asymmetric because we've got 2 hydrogens on one carbon but a hydrogen and an ethyl on another carbon, then we're going to make chiral products, 2 possible chiral products. Both of them have got that regio-specific reaction in which the bromine is going on to the more substituted, in this case carbon 2. Okay, but it can, the bromine can attack from the top on the carbocation or the bottom from the carbocation, and if you end up with a chiral carbon, once you've done that attack, then you will get both enantiomers. You will make a racemic mixture. Okay, some of that discussion, a little bit more than the A level, but I think it's worthwhile to take through the final parts of a mechanism, just so that you're always thinking about the structural issues in what you're doing. Now, the next little video associated with this is a extension. In fact, it might even be, it's going to be right after it in the module list, so that those who want to can watch this Markovnikov hydrobromination, in which the bromine goes on the more substituted carbon, but you can see as part of the extension material, because it's definitely not on the A level, how all you have to do is tweak it ever so slightly and you'll end up making the anti-Markovnikov product. However, that's the next movie. Those who don't want to do the extension, just skip that movie and move on to the next one, which is all about bromination of alkenes.